In this video, I introduce least square methods for neural network training. Neural networks are trained on a set of training data to run a general transformation from a set of input variables x to a set of output variables t. The neural network training is not to memorize the training data, and instead the trained neural networks are able to predict the correct output label given a new input value x through the probability density p in the joint input target space. Using the probability chain rule, the joint probability p is decomposed as here, where p t conditioned on x is a conditional probability of a target t condition the input x, and the unconditional probability px has a margin of p xt over the target t. The goal of neural networks becomes to model the conditional probability of t condition x. Training neural networks becomes to minimize a sum of squares error es between the prediction and the target over a set of training data to approximate the conditional average of target data as shown here, where W is the network parameters and Fk is output of the neural network models. Using finite size of neural networks and finite scale of training dataset will introduce bias and variance. If the sum of squares error is written as integral over the joint probability as shown here, the minimum of ES is obtained by forcing the derivative of ES with respect to Fk to be 0 as shown here, which is satisfied under the condition. Where Tk condition X is a conditional average of target data Tk and W asterisk is the optimal weight values. Therefore, the network function Fk is given by the conditional average of target data condition on the input data as shown here. There's a neural network, this input, this output Fk, and given X, we have this output Tk. They follow the distribution P out of T condition X. Substituting Tk condition X into ES using the chain rule, the error function ES is rewritten as a sum of two terms, this term 1 and this term 2. Notice that the error function only depends on the model weight W in the first term, as shown here. And its global minimum is given by the conditional average of the target data. The second term gives the residual value of error function as a global minimum. Assuming that the conditional distribution of target data is Gaussian, as shown here and here, where sigma square is a global variance and Fkx is the mean of a target variable Tk. The least square can be obtained by using maximum likelihood method, and the weight W is determined during the neural network training. Assuming that training data are driven independently from a Gaussian distribution, the likelihood error of the training dataset is given by this formulation. The model weights are obtained by maximizing the likelihood error. In practice, we equivalently minimize the negative logarithm of error, namely E is equal to negative logarithm error, since the logarithm is a strictly monotonic function. Modeling capital F key by F key, the error function E is written as here. Note that only the third term, as shown here, depends on the weight W. To minimize the error function E, we only need to minimize the third term here, omitting the factor sigma square. The standard sum of squares error function used in neural network training, as shown here, using the W asterisk and the derivative of E with respect to sigma. We got the covariance here. For more details, please check with these references. Thank you. Bye.